So in this video, we'll look at the integration of the trigonometric functions where the functions are tangent x and secant x, and both have certain exponent m and n up on top of them, and m and n are some positive integers. And I claim that the easiest case to solve here is the case where n is even. So I don't care about the m. M doesn't matter to us. As long as n is even, I claim that we can solve it quite quickly. The fact is that we always have to use the u substitution now, and u is gonna be tangent x in this case. Let's see why it works. Let's look at an example together. So please look at the current example where we have the power of tangent x to be 3 and the power of secant x to be 2, and it satisfies our criterion. You see, because we don't care about the power of tangent, we only care about the power of secant, which is 2. Of course, 2 is even. I claim that we can use u equals tangent x, right? And as a substitution problem, you have to write down du. And du is the derivative of tangent x, which is secant square x. And we have to make use of this now. And we have to convert everything in x to u inside the integral. And surprisingly, it is quite convenient because of what? You see this part is what? This part is just du, right? The key is that du actually take out 2 copies of secant x. And in this case, we only have 2 copies of secant x, right? So they are all taken out by du. And the remaining terms is tangent cube x, because u is actually 1 copy of tangent x. So tangent cube x is actually the same as u cube, right? So this problem, essentially, you're asked to integrate u cube. Simply by a power rule, we are able to write the answer down, which is u to the power 4 over 4 plus a constant c. And you may be wondering how we can do such problems if, let's say, the secant actually has a higher even power. And let's look at the next problem. So please look at the current problem now. The tangent x actually has power 2, secant x has power 4, right? And it is still even. So I claim that our method still works. So let me write it down on the right hand side. U is tangent x, which means the u is actually secant square x times dx. And let's see how it works. The fact is that the du actually takes out 2 copies of secant x, and it means that we can pick out 2 copies of secant x from the secant power 4x. It's like this. So 2 copies are absorbed by the du. So remaining, we still have an power for the secant x, right? And let's change everything to u. Tangent square x is clear because u is tangent x. So the first term is going to be u squared. And the middle term, you have to make use of a very famous trigonometric identity, which is 1 plus tangent square x is the same as secant square x, which means that because u is tangent x, which means 1 plus u square is going to be secant square x, right? And I write it here, which is 1 plus u square. So I claim that you're able to do this integration because, let me write it down here, you're just integrating u square open bracket 1 plus u square close bracket for du. And of course, I can distribute the u square in. So essentially, you're integrating u square plus u to the power 4. And simply by a power rule, the answer can be written this way. And of course, u is tangent. So I just replace u by tangent x. And it is our final answer to this problem. As you can see, even if the power, please look at the first line, even if the power for secant is a bigger even number, let's say 6 or 8 or 10, it doesn't matter. The fact is that we still use the same substitution for the u. And after taking 2 copies of the secant out based on the du, you still have an even number of copy of the secant. And in that case, we can always make use of the identity for the purple star to change everything into the u substitution. And you are always able to integrate this by some algebra to expand it, maybe by distribution, etc. Anyway, that's the key to this problem.